Swayam Prabha. Digital India. Educated India.
Hello everyone. So today we are into the third lecture of our module number 8 or the week number 8, where we are talking about the breeder reactors. We already had 2 lectures, so I am sure you by now know the concept of breeding and also have started to understand the difference between of a breeder reactor with a conventional thermal reactor. Just to have a quick recap, in the previous 2 lectures we have discussed about the concept of breeding and also the breeding ratio. Now, we know that the term breeding basically refers to a reaction like this, where a fertile nucleus absorbs a neutron and that goes through successive decay processes. In fact, I should not say all the breeding reaction involve such kind of decay, but the common reactions like those involving uranium 238 or thorium 232 is always in these cases you will find such kind of decay, that is one neutron absorption step followed by 2 successive steps of beta decay leading to the final product of plutonium 239 in this case. And when it starts with thorium 232, then after absorption of the neutron we get thorium 233, which goes through 2 successive steps of beta decay to produce uranium 233. But there can be other kinds of other kinds of breeding reactions as well, which are direct, like plutonium 238 can absorb a neutron to produce plutonium 239, or more commonly plutonium 240 can absorb the neutron to produce plutonium 241, which such kind of direct single step breeding reaction is also possible. But generally the 2 most common kind of breeding reaction that you will find in industries, one referred to the one that is shown here, uranium 238 absorbing a neutron to produce plutonium 239, and the other one which is of increasing popularity, where thorium 232 absorbs a neutron to produce uranium 233. As I have already discussed that thorium reserve in the world is at least 3 times more compared to uranium, and therefore, and its primary isotope is also thorium 232, just like uranium 238 in case of uranium, and therefore, several countries are looking to build their future plan of action in case of nuclear power generation based upon thorium, which involves India as well. Like Indian nuclear power program has a big dependence on thorium. India has quite a small stock of uranium, but very large stock of thorium, and therefore, we shall be talking about later on in the next module, where you will find that the thorium 232 plays a big role in Indian nuclear power program, where we use this particular breeding reaction to produce uranium 233, and subsequently that uranium 233 is used as the primary fuel isotope. And breeding also plays a very important role in showing the prospect of nuclear energy for future. While the stock of uranium is quite limited, only through the breeding we can still continue to use nuclear power for something in the range of 25 to 30,000 years, which is near infinite considering the present scale. And also, as one particular isotope, which is uranium 238, which before up to this module was thought about of no use at all, it can be found to be of great significance through this breeding reaction. Like earlier, whenever you have discussed about factors like resonance absorption, you must have always felt that that is a loss, because uranium 238 has a very high resonance absorption cross section at certain energy levels. Therefore, when a neutron of that energy level comes in contact with an uranium 238 nucleus, that immediately gets absorbed, which we have called resonance absorption, and immediately that neutron goes out of the system, because that is no longer available to become thermalized and cause any kind of thermal fission. but that neutron which has been absorbed by thorium to uranium 238, that actually can lead to this breeding reaction, thereby adding some more fuel into the system, and hence that is also of great importance. And as a result, a reactor, a thermal reactor which is fueled only by uranium can still have 30 to 40% contribution in the total power production coming from the plutonium, and plutonium is entirely generated inside the reactor alone. Breeding ratio we have defined as the ratio of the number of fissile nucleus present after a reaction divided by number of fissile nucleus consumed during a particular reaction, and when a reactor is having a breeding ratio greater than 1, then only we call it a breeder. We have discussed about fuel cycle and the neutron or uranium enrichment process in the previous lecture. While we get only raw uranium ore from the mines, that needs to go through the milling and conversion processes. At the end of the conversion processes, we get uranium hexafluoride gas, which goes through this enrichment process. There are several ways we can achieve enrichment. Basically, enrichment refers to a process which increases the fraction of uranium 235 in the total mixture. And out of all the possible methods, this particular one, which is the gas centrifuge, is the most popular one at the present, but the laser one also, the laser based method also has a great future ahead probably. So, once we get a stream of uranium which is enriched, that is which has higher fraction of uranium 235, that is subsequently taken to the nuclear plants or nuclear reactors for utilization. And also, once the entire process is done, the spent fuel that we get out of the reactor, that can also contain significant amount of fuels itself. Like say, if we are starting one reactor with natural uranium, then after going through the process for a prolonged duration, something like 1 year or 3 years, whatever we get back at the end, that still contains about 97% of uranium 238, about 1% or slightly less than 1% of uranium 235, about 1% of plutonium 239, and rest, or I am actually a bit wrong, means initially about 95% of uranium 238, nearly 1% of plutonium 239 and uranium 235, and rest 3% generally corresponds to the fission fragments, those fission poisons, etc. So, still there are about 2% of that mixture which can further be utilized as fuel, like that 1% of uranium 235 and 1% of plutonium 239, and the spent fuel reprocessing generally focuses on separating out those fissionable nucleus from that mixture, and also removing that 3% of fission fragments from this, because that is generally of no use. That fission fragments goes for some further waste disposal, which is the topic of our last module, but the useful components, that is that uranium 235 and plutonium 239 that are reprocessed, Purex is one particular procedure which is which has been standardized through the years, and at the end of such a process like Purex, we generally have two kinds of products. One is pure uranium oxide and other is MOX or mixed oxide, which contains both uranium oxide and plutonium oxide, and that can go for further utilization. We have also discussed about open, closed and hybrid fuel cycles. In open cycle, there is no reprocessing. So, it is a once through, it is just a once through process. In case of closed cycle, however, we generally have both thermal and fast reactors involved. The waste coming out of the thermal reactor is sent through the pyroprocessors and recycling plant, and corresponding output is fed to the fast reactor, thereby producing some more fuel for future use. And a hybrid plant, though it is only a thermal plant, but it generally utilizes both uranium oxide and MOX for its power production. Then we have discussed about the characteristics of FBR and also compared its performance with a classical pressurized water reactor, and finally, we have discussed about the pool and loop type designs of the FBR. Both have its own advantages. In case of pool type, we have everything like the the reactor core, the primary pump, and also the heat exchanger or intermediate heat exchanger, all immersed into a pool of liquid fuel, that is generally liquid sodium, whereas in case of loop type design, the pump, it is only the reactor which is immersed into the liquid sodium. Both the pump and the intermediate heat exchangers are kept outside. Both designs have its own advantages and therefore are being used in different designs. So, today we are going to finish our discussion on the breeder reactors, and then to facilitate that, we shall mostly be discussing about the coolants that we normally use in breeder reactors. But one question I should answer at this point, that why we are talking about breeder reactors in such depth. Like in the previous module, we talked about thermal reactors, and there are several types of thermal reactors available, like the pressurized water reactor, boiling water reactor, pressurized heavy water reactor, gas cooled reactor, or the RBMK group, which is graphite moderated light water reactors. So, there are so many variations, but still we went through them quite quickly and finished that module in just 2 lectures. But in this FBR group, we are discussing in more detail and taking our time to discuss. That is because of this generation 4 initiative. Under generation 4 initiative, which basically proposes the future nuclear reactor designs, which are going to rule the power production industry in the years to come. If you remember from our previous module, there are generally 6 reactor designs which are found to be very prospective under this generation 4 initiative. The one of them is this VTR or VHTR, very high temperature reactor. We have discussed its characteristics earlier, but of course, none of the generation 4 reactors are active at the moment. While some of them are restricted to the research laboratories, some of them are only a concept and has gone through theoretical analysis or very small scale test runs. Now, from the knowledge base that we have gained from there, the VTR shows that it has a very poor fuel utilization performance. In fact, its utilization performance is quite similar to the present light water reactors, the thermal reactors, and it does not offer any extra advantage of like we get in case of FBRs. In fact, VTR generally is a thermal reactor only, and therefore, it is only expected that its utilization performance will be similar to the modern day thermal reactors like PWRs. So, the other one is SCWR. Of course, it is very promising because it works at the supercritical pressure and temperature level, and so promises very high thermal efficiency, something in the range of 44 to 45%, but it has own issues like very high pressure and temperature, and also from fuel utilization performance point of view, its utilization is lower compared to the present FBRs. The present design fast reactor shows a much better utilization of the fuel, and better fuel utilization means much less amount of waste product. So, lesser effort is required for the waste disposal. SCWR fails in that category. And as the fuel utilization is poor, so it requires much larger fuel inventory, particularly the plutonium inventory requirement, and also it has some questions raised about the plutonium breeding capability, which still needs to, or it is still not in a position to demonstrate a very high breeding ratio, and therefore, doubt remains whether we at all can go for this SCWR in future, because whatever future reactors we are going to have under this generation 4 or maybe even future generations, we must ensure that breeding, a proper breeding ratio or high breeding ratio is a must, so that we can get a good fuel economy, a very high utilization of the fuel, but both VHTR and SCWR fails in that category. And the other one is the molten salt reactor. Here the knowledge base is quite small. In fact, the technology itself is not very matured, and still lots and lots of R&D is required on MSR before it can at all be realized. It is still a concept which has hardly got tested at the laboratories, and as the molten salts are used here, so there will be a big amount of corrosion problems, and safety issues or maintenance issues are also very much prevalent for MSRs. Therefore, out of the 6 designs selected in generation 4, at least or these 3 have their own issues, which leaves us with the remaining 3, that is SFR, LFR and GFR, or namely the sodium cooled fast breeder reactors, lead cooled fast breeder reactors and gas cooled fast breeder reactors, which have given priority in future design and development, and incidentally all of them are fast reactors, and that is the reason we are discussing so much in fast reactors or fast breeder reactors, because fast breeder reactors are the future. In the present day, that is under generation 2, all those PWRs and BWRs or all those thermal reactors that we are using at the moment, in next 3 or 4 decades to come, they all may get extinct, and slowly but surely they will all get replaced by the breeder reactors. And that is why it is very important to get some more idea about the breeder reactors. Now, most common design of breeder reactor is this LMFBR or liquid metal cooled FBR. And this particular picture we are seeing from the beginning only, where we are using a liquid metal, generally liquid sodium as the coolant. This design, can you guess it is a pool type or loop type? Sure, it is a pool type design, because here you can clearly see the reactor core, the primary pump, and also this intermediate heat exchanger. All of them are immersed into this big pool of sodium, big pool of liquid sodium. So, as they are all immersed into this big pool of liquid sodium, we call it a pool type design. The cold sodium or cold liquid sodium is allowed to be pumped through this line into the core, where they gets the energy. So, becomes high temperature sodium, which is termed as the primary sodium here. And this high temperature liquid sodium passes through this intermediate heat exchanger through this line, and there it passes its energy to a secondary heat exchanger, where the working medium is also liquid sodium. So, the liquid and then this primary sodium comes out from here and then again gets pumped through back to the core. But the liquid sodium which is flowing through the secondary circuit, that comes via this line and then gets the energy and then goes back side, and then it goes to the other heat exchanger, which is basically a steam generator. Here on the high temperature side we have this secondary sodium, which has just come out of the intermediate heat exchanger with large amount of energy, and on the primary side we have liquid water which comes through this pump, and then as it passes through this heat exchanger, it gets the energy, thereby gets converted to steam, and finally that steam comes out of from here to go to the turbine and gives the electrical output through the alternator or generator. So, this kind of liquid metal cooled fast breeder reactor is the most common design, and whatever FBRs that you can find throughout the world, now there are only very few countries which are working on FBRs, which includes Japan, China, India and Canada, and of course Russia, where the whatever FBRs they are having, they are all of this liquid metal cool type, and liquid sodium is the coolant that is universally being used. It is not that other fluids have not been tried, rather some early day reactors employed mercury as the fluid, and also some research reactors are using this sodium potassium alloy as the fluid. One big advantage of both of them are both mercury and the sodium potassium alloy, they are liquid at the room temperature, but sodium is not liquid at room temperature, it has a melting point of around 98 degrees Celsius. So, once we can use a material like mercury which is liquid at room temperature, directly we can apply this to the reactor, and that is very suitable for small experimental test rigs or research laboratories. But when you are talking about the industrial scale, there basically that is irrelevant, because anyhow we are working at the high temperature, and there is not very many, and there is very less probability that the temperature will fall below that 98 degrees Celsius. So, sodium will always remain under liquid condition. But a more prospective fuel can be lead or lead bismuth eutectic alloy, which is also called LBE alloy. Sodium of course is universally used in FBRs, but it has its own issues, like it has a relatively low boiling point compared to lead or other materials. We shall be seeing the numbers shortly, but its boiling point temperature is quite low. Then the biggest issue, sodium is highly chemically active. Whenever it comes in contact with either air or water vapor, it immediately starts to react, a highly exothermic chemical reaction, and that is always accompanied by a fire. and therefore sodium must be kept separated from the steam which we are using here as the working medium of in the final turbine generator circuit. That is the reason of having this intermediate heat exchanger. The sodium that we are heating up in the primary vessel, or in the pool, that sodium can't directly come out and supply or exchange energy with the steam in the steam generator. Rather, we are using the secondary sodium loop which is operating at a lower temperature level, and also that provides some kind of safeguard, so that the sodium is never coming in contact, sodium in the primary side at least, that is never coming in contact with the water or water vapor. The mean free path of neutron inside sodium is much larger, which increases the possibility of leakage as well. And finally, another problem which happens generally in the energy interval of 0.7 to 1.5 MeV, the scattering cross section of sodium within this particular energy level is quite high, both elastic scattering and inelastic scattering, and therefore there is possibility of some kind of moderation effect that may come in when the neutron falls in this particular energy band. So, these are quite a few drawbacks that we should be careful of while using sodium as a coolant, but sodium has its own advantage also. For that, just take a look at this table. Here we are comparing the coolants which are commonly used in generation 4 fast breeder reactors. Sodium is the coolant for SFR, lead or lead bismuth eutectic are generally thought about for the LFR, and in gas cooled reactors we may use carbon dioxide or more preferably helium. Look at their properties. Both sodium cooled reactor, that is SFR, and LFR comes under the liquid metal cooled FBR category, whereas CO2 and helium are used in gas cooled reactors. Now, first let us take a look at the melting and boiling point data. Sodium has a melting point of 98 degrees Celsius and a relatively low boiling point of just around 883 degrees Celsius. Compared to that, lead has a boiling point of 1737 and lead bismuth eutectic is also quite similar. So, they have extreme very high boiling point and thereby allowing the coolant to reach much higher temperature, whereas when you are operating with sodium, the final coolant temperature has to be lower than this value. In fact, should be reasonably lower than this value, maybe hardly allowing something like 800 or 820 degrees Celsius, whereas with lead or lead bismuth eutectic we can go easily up to 1500 degrees Celsius without ever bothering about the cooling or rather the phase change of this coolant. The another point that we should consider, which actually is favorable to sodium. Sodium has its own advantages because it has superior thermal hydraulic parameters. Its melting point is not of any consideration, but boiling point is, but apart from that all other thermophysical properties of sodium are excellent. Like, look at the thermal conductivity. Its thermal conductivity is 64 watt per meter Kelvin, which is just in the order of 15 for lead. Similarly, if you take a look at the say rho Cp product, which is also called the heat transportability or heat capacity, it is also quite good for sodium. Of course, lead is even better, both lead bismuth eutectic and pure lead, they are even better. Specific heat for sodium is much larger to 1270, which is significantly higher than lead. Another big issue that we may have using liquid lead as the working medium, sodium is a very light metal. So, look at the density of sodium, it is around 825 kg per meter cube and this is 10,000. So, is this one. So, it is about 12 to 14 times more dense compared to sodium, and as it is as the density is much larger, so that in that proportion the pumping power needs to be enhanced, much larger power will be required to drive this liquid lead or liquid lead bismuth eutectic mixture to flow through this coolant channel or maybe through the circuits or through the zones around the core, and there will also be chance of pipe clogging because of its high density. So, from all this point considering, sodium has superior thermal parameters, and apart from the boiling point, once we can restrict the highest temperature, it is definitely more suitable fluid compared to lead. Melting point is very low. Lead has a melting point of 327 degrees Celsius, 327 degrees Celsius compared to just 100 degrees Celsius. Therefore, while the upper working temperature or allowable working temperature on the higher side is very high for lead, but the lower side temperature is also quite high. The operating temperature should be something like 350 degrees Celsius or higher, the lowest operating temperature. And so, we have to generally handle much higher temperature level in LFR, and the coolant temperature in no case should fall below that 350 degrees Celsius. The temperature range applicable for sodium is reasonably wide, like if we compare this range, still we are getting a range of about 700 degrees Celsius, but the range definitely is much larger in case of lead, where I can find it is around 1400 degrees Celsius. So, if such kind of high temperature change is desirable, then we can't go for sodium, we have to go for something like lead or LBE. LBE refers to lead bismuth eutectic. But another advantage for sodium is, as the melting point, as long as the boiling point can be managed around that 883 degrees Celsius, or I should say as long as the maximum coolant temperature requirement is well below that 883 degrees Celsius, we do not need to go for any kind of pressurization. The system can operate under atmospheric pressure only and still allow a decent temperature range for operation. Sodium is definitely inexpensive, and also it is compatible with stainless steel. Therefore, there are several points which generally make sodium the most suitable coolant, but lead is also not far behind. Lead is the biggest advantage is compatibility with air and water. The biggest problem for sodium, as I have mentioned earlier, it is highly reactive, particularly in contact with air and water, it reacts immediately and starts to burn on its own. But lead does not have such level of chemical activity. It is very compatible with both air and water, and therefore, we can use the lead cooled reactor or LFRs with even open to atmosphere also, or I should not say open to atmosphere, I should say in case of LFRs we do not need to have that secondary loop or intermediate heat exchanger loop. In case of SFR, we need that intermediate heat exchanger, because the primary coolant, which is liquid sodium, that should not come in contact with the water which is flowing in the external circuit. That is why we use that intermediate circuit, where the working medium is again sodium, but working at a much lower temperature level, and that can supply energy to the coolant. Another advantage for lead is very high boiling point, which I have just mentioned. We can easily go up to 1600-1700 degrees Celsius. Heat capacity for lead is larger, like if we compare the heat capacity, it is 1510, it is 1463 for LBE. So, about 50% larger than what we get with sodium. And what can be the advantage of having a high heat capacity? I hope you can guess, because we know that for any incompressible liquid we can always write Q equal to mCp delta T, or delta T is equal to Q by m into Cp, and if we break the Cp, then becomes cross section area, rho Cp into cross section area into the velocity of the liquid coolant, and therefore, higher the rho Cp value, the smaller will be the temperature difference of the coolant. But lead or LBE both have quite high heat capacity compared to sodium, and therefore, they can be more preferable from temperature rise point of view. Sodium lead, like similar to sodium, can also allow low pressure operation. It is also inexpensive and quite easily available, but lead has its own issues. It is chemically toxic, which sodium was not. It is chemically toxic, and its melting point is very high, like 327 degrees Celsius here. So, in no case the coolant temperature in the core should fall close to 327, it should always remain something like 350. Another problem is heavy and corrosive. It is extremely corrosive, and so can damage the metals of the walls. And if we talk about LBE, LBE shares most of the issues of lead. Means from advantage point of view, again its melting point is lower than lead, but not by a huge degree, and so that is quite decent. Or I should say the melting point of LBE, while it was 327 for lead, it is just 125 for LBE, which is quite close to the value for sodium, and therefore, it is much easier to use LBE, and we can allow the temperature to drop to something very close to the ambient temperature. Or okay, let me correct, melting point being so low for LBE, we can easily operate at much lower temperature level compared to lead, but it has other advantages, like similar to lead, it is chemically toxic, it is heavy and corrosive. Then there has been maintenance issues. LBE has not found used in power reactors so far, but there are a couple of examples where LBE has been used as the fuel in nuclear powered submarines, in Russian submarines, and both cases maintenance issues were found. There may be some other reasons also, but on those two Russian submarines, both reported severe maintenance issues, and that was related to the flow of this LBE itself. And bismuth is not that easily available. Lead of course is easily available, but bismuth is quite scarce, and also it can become active under neutron flask. Bismuth can participate in a reaction like this. The Bi209, which is the most common isotope, can absorb a neutron to produce Bi210, and then it can go through a beta decay to produce polonium-210. But sodium, if we compare with that can also participate in such a reaction, like sodium-23, which is the most common isotope of sodium, which is available in the nature in the form of natural salt also, sodium chloride, that can absorb the neutron to produce sodium-24, which is highly reactive and immediately goes through a beta decay process to form magnesium-24. And you can see the half-life value for sodium-24. Its half-life is quite small, it is just about 15 hours. Therefore, from the point at which the sodium-24 is formed, almost within about 15 minutes, half of those new nucleus or new nuclei will break down or will participate in the beta decay to form magnesium, and it is expected that this or we can visualize this conversion of sodium-23 to magnesium-23 to be almost direct because of this small half-life, and magnesium-24 is a stable isotope. So, the radioactive effect of sodium-23 inside the reactor is not that significant. But if we compare that with bismuth-209, then half-life of bismuth-210 is more than 5 days. So, some more time is required to remove the radioactive waste from the reactor, and also the radioactive waste or products like polonium or etc., which remains inside the reactor, that, or I should not polonium, I should say this Bi210 now has more time inside the reactor to participate in the radioactive decay, thereby emitting or thereby causing the probability of more radioactive hazard. So, in a nutshell, whatever we are getting from this slide and the previous slide, sodium has its own issues, but still it is the most suitable coolant that we can identify at the moment, and that is why so the liquid cooled fast breeder reactors whatever we have at the world at the commercial level at the moment, they all work with liquid sodium. So, we come to the sodium cooled fast reactor SFR, its characteristics were discussed as a part of the previous module. Now, we discuss about some issues that it may have. The sodium has its own advantages as we have mentioned, but SFR also facilitates for a couple of advantages, because of which it goes for the full type operation. Pressure inside the pressure vessel is can be quite low. Sodium has a low melting point and reasonably high boiling point, and therefore, we can operate this in unpressurized situation, and pressure vessel can remain at the atmospheric condition. Another problem that, or another advantage rather, SFR possesses is a minimal risk of leakage of the primary sodium, because the way it has been designed, the primary coolant will not leak out the core. But there are several issues which also need to be sorted out before full commercialization. Actually, out of these three, SFR, MFR and GFR, SFR is the one whose development is at the most advanced stage. The trial runs all are completed and it is presently gone for the power testing, and once the power testing is successful, then probably it can go for full scale commercialization. But the issue is that sodium circuits and steam generators demand early detection of leaks and robustness in managing their consequences, because even a smallest amount of leak of sodium out of the reactor will bring it in contact with the atmospheric air, which can lead to fire inside the plant. The complexity in service inspection and repair, sodium is opaque in nature, and also we should never allow the sodium to come open to the atmosphere, and that is why in service inspection or when the run is going on, when the reactor is operating, that time any kind of inspection and repair is impossible. SFR can offer an intrinsically positive local void effect, as it is using a liquid fuel. If temperature fluctuates inside, then there may be small void of sodium appearing, or small sodium vapors may start to appear, and if we are having a positive local void effect, then that can lead to a failure of the reactor. So, that is something that needs to be managed generally by optimizing the design of the core. And finally, the improvements in the prevention and consideration of risks of severe accidents and on the robustness of the safety demonstration, which also needs to be ascertained for this SFR. Next, we have the LFR, lead cooled fast reactor. The biggest issue with LFR is its highly corrosive nature. Lead has its own advantage over sodium, like I have mentioned. It has much higher boiling point and it has a higher heat capacity, but its melting point is also high, and it is also corrosive in nature compared to sodium. So, lead as a fuel has or rather as lead as a coolant has its own advantages and disadvantages, and along with that the LFR itself also generally, because of the high temperature involvement, we like to use stainless steel as the material, and this lead is highly corrosive to stainless steel, which is the biggest issue LFR immediately faces. Only reasonable option to prevent such kind of corrosion is to use a protective layer of iron oxide on the inner surface of the stainless steel. The surface which is in contact with lead, that we put a protective layer of iron oxide, so that the lead is not coming in contact with the steel. But this particular technology can require quite a few factors, like accurately managing a very low concentration of dissolved oxygen, about 0.01 ppm, maintaining the temperature at every point in the system between 400 and 480 degrees Celsius. This is quite a narrow band, but we have to maintain this, because if the temperature falls below this 400 degrees Celsius, then there will be risk for structural corrosion, whereas when it goes above 480 degrees Celsius, then certain steel may become quite brittle. And also purifying the insoluble lead oxides and corrosion residues present therein. That is another thing that we have to consider. If this iron oxide layer can't properly be implemented, then there can be serious accidents like those two Russian submarines that I mentioned earlier, which are using lead bismuth eutectic kind of material as coolant. Because of the clogging or fuel assembly meltdown, the entire reactor performance may get affected. The erosion of the steel cladding by lead can be limited if we keep the velocity small, something less than 2 meter per second. But also if we reduce the velocity, that will reduce the total flow rate of the lead. But once the flow rate reduces, for a given power output, the temperature rise of lead also will increase across the core, and that is also not desirable. And therefore, to cool the core properly, we need to go for a much wider flow section. And as we are going for a wider flow section, in order to allow the required amount of mass flow rate of lead, so that it can take the power output, the total power density and hence the neutronic performance becomes poor, leading to low capacity designs compared to PWRs and BWRs. This capacities is quite low, or I should say mostly compared to SFRs, this capacity is a bit low. Also, there are issues related to LFR itself, like in service inspection against because lead is opaque and both sodium and both cases, so is sodium, and both cases this in service inspection may become difficult. The corrosive environment is another issue because of this in service inspection. Behavior of molten coal in severe accident situation, that is something that has not been studied at all. The limited database is quite limited, and therefore we have to study that. Particularly, we have to consider that the lead is much denser compared to both the fuel and steel, which is the cladding material. The design of the systems and particularly earthquake resistance, given again the very high density of lead, can be the factor there. And finally, aerosol management, washing and decontamination techniques needs to be considered. Finally, the gas cooled reactors, the GFR, it combines the advantages of the fast neutron technology, because the material management in fast neutron technology is very high, resources can be conserved, and so is the waste. Neutrons, once you are going for fast neutrons, we can facilitate breeding, therefore resources can be conserved, we shall be having much less amount of waste, so waste management becomes easy. But also GFR allows to us to go for very high temperatures, as we are using a gas, commonly helium. In certain cases carbon dioxide as a working medium, we never have to bother about any kind of boiling temperature limit, unless there is any kind of stability issues or chemical stability issues at elevated temperatures. We can keep on increasing the temperature level, and at high temperature level thermal efficiency keeps on increasing, and also non-electricity generating processes can also be facilitated. That is, we can go for some kind of cogeneration as well. Like you can look at this diagram, the hot gas, that hot helium gas that is coming out of this, that generally goes to the turbine, and from the turbine it goes to the recuperator, and the turbine, after doing the expansion work, it goes to the recuperator, and from the recuperator it goes back. But the gas that we have in this recuperator, or I can say the material or the fluid which is taking the heat in the recuperator, can also be used for other purposes, like such as for cogeneration. And also another advantage with helium as the fluid is we are having an inert and transparent coolant. So in-site inspection or any kind of maintenance is very easy. It is an inert environment, so no problem with any kind of corrosion or any kind of chemical reaction when it comes in contact with water or air. But the heat transfer performance of course will be poor, because their thermal conductivity is significantly lower, almost negligible compared to that of sodium or lead. There are two main technical issues with GFR, one with the fuel and other is accident management. Related to fuel, we need to find a proper mixed carbide fuel, which will be put in a silicon carbide cladding, and that should be capable of sustaining up to 1600 degrees Celsius without any buckling, so that the fission products can be maintained. Other is the regeneration of fissile fuels without any kind of radial blankets. And finally is the development and qualification of ceramic cladding, which can remain operational for several years, which is not possible with the present day material science knowledge. And with accident management, GFR should demonstrate that the cooling capacity can be maintained in case of a primary break. Also, dedicated safeguard mechanism is required to limit any kind of consequences of such cooling related accident. And also how the core material is going to behave at very high temperatures or also varying pressure, that is unknown. So, that is something that also we should look into. So, and finally, the technological feasibility of GFR should be ascertained before commercialization. So, in a nutshell, we can say that all these three fast breeder technologies, that is SFR, LFR and GFR, all of them show immense possibility and future can be the solution for power requirement in future, but still there is some way to go because we have to sort out quite a few issues. That brings us towards the end of this module, but I would like to finish with a small numerical example related to this breeding ratio. Let us consider we have a breeding reactor which is filled up with uranium oxide as a fuel, a certain quantity of uranium oxide, which has 2% of enriched uranium. And you have to calculate the conversion ratio after 6 months of operation if it is subjected to an uniform neutron flask. Now, 2% enriched uranium means the fuel contains 2% of the fuel contains 2% U-235 and 98% 238. Other isotopes of uranium like U-234 etc. can be neglected. So, what are the isotopes that we have inside the reactor? Of course, when you are starting with, we are having U-235, U-238. U-235 will go for fission reaction, thereby will produce the fission fragments, and U-238 will participate in the breeding reaction. So, as time goes on, we shall also be having Pu-239 produced inside the reactor. So, initially Pu-239 concentration is 0 to start with, but as time goes on it will keep on increasing, whereas concentration for both U-235 because of fission and U-238 because of this breeding reaction will keep on coming down. And actually plutonium concentration we are not sure that it will continue to keep on increasing, because it will increase because of the breeding, but it will also decrease because of its own fission decay. If you just go back to the module number 6, there we made a small mathematics to discuss about the control issues, and there we identify this expression. N25 refers to the concentration of uranium 235 nucleus and how it changes with time. This one being the initial concentration. Then N28 refers to uranium 238 concentration. This is again the initial one. In this case, this is 98%, and plutonium concentration is initially 0. So, this N49 refers to Pu-239, and these are the corresponding cross section values. So, using this, our time period, this T is referred to as 6 months in this case, and as we already know the molecular weight or the mass number for all these three isotopes, so we can always calculate the value of this N025 and N028, and phi and all the sigma values are given. So, at the end of 6 months of operation, we can calculate the values of these three quantities, and now conversion ratio at any time is given like this. So, using this you can calculate the conversion ratio. I am leaving this to you. Please try to solve this problem, and if you face any issue, then you can get back to me. So, to summarize our observation from this module, we know now that breeding refers to the transmutation of a fertile nucleus to a fissile one, which can act as a fuel for another reactor or maybe in the same reactor. Conversion ratio greater than 1 signifies a breeder reactor, whereas when it is less than 1, we generally get burners or converters. And doubling time is the time which is required to make the number of fissile nucleus double than whatever we had initially. Then we have also discussed about the thermal fission factor and temperature, the role they play on deciding this breeding ratio. Then we discussed about the fuel cycle, and we have seen that in all the processes, generally the mined uranium is converted to uranium hexafluoride gas through milling and conversion, and then we go for the enrichment process. Gas centrifuge is the most preferred method of uranium enrichment. Then FBR offers much higher power density and compact designs compared to the thermal reactors, but it requires much superior control. We have discussed in detail about the pros and cons on FBR and also its comparison with the PWRs or thermal reactors in general. SFR, MFR and GFR, actually instead of MFR, I should not write MFR here, it should be LFR, the lead cooled fast breeder reactor, or if we write properly, this should be LFR. SFR, LFR and GFR are the most promising designs under Gen 4 initiative, because the other 3 designs have their own issues, but all of them had to solve certain technical issues before final commercialization. So, that brings us towards the end of the module number 8. Please go through all the lectures and solve the assignments, which is also available with you, and whenever you have any issue, have any doubt, please drop a line to me. So, thanks a lot. In the next lecture, in the next week, we are going to discuss about the other type of nuclear reaction possible, about which we have never talked about since our first module, which is fusion power generation. So, thank you.